In this section, we're going to look at limits again. And I'm not going to mention like everything. I'm not going to explain everything, but I'm going to try and touch on the, I guess, the tricks that we've used, and also I'm going to try and touch on things that people tend to forget. The first thing, it seems really simple. It's just the limit of a constant is just that constant. So, an example, the limit as x approaches 4 of 25 is just 25. Doesn't matter that what x is approaching. This is just saying, like, I have the function y equals 25, and that would be the line that crosses at 25. Well, when x is 4, yes, y is 25. Or when x is 10, y is 25. When x is negative 3004, y is 25. So, limit of a constant is just a constant. And there we go. This is kind of going to go fast, I hope, at least. So, we're moving on. Another thing I want you to remind you of is for indeterminate forms, like 0 over 0, infinity over infinity. Those are special ones. Those ones you can use L'Hopital's rule for, if you have those. So those ones are special. Maybe I'll circle that in red. Or infinity minus infinity, or 0 times infinity, or I think 0 raised to the infinity, or infinity raised to the 0 power. Those ones, they're indeterminate forms. You can try factoring, force factoring, multiplying by radical conjugate, or L'Hopital's rule. Remember, you can only use L'Hopital's rule if you have those indeterminate forms. If you have the other indeterminate forms, you might be able to get it into this form. But yeah, that's another thing that you need to remember. I feel like once students learn L'Hopital's rule, they rely on it very heavily, which is fine, I guess. But don't forget that you have to have that form to be able to use L'Hopital's rule. Otherwise, you should use these other tricks. For some of these, you could also use the squeeze theorem. But if we know L'Hopital's rule, it takes care of the squeeze theorem fairly easily, and I feel like more people would remember that. So, yeah. If you wanted to, you could look up proofs of the squeeze theorem. It's actually really interesting, but it's faster to remember L'Hopital's rule and just use that. That's one of the special cases for the squeeze theorem, but this equals 1. You could just use L'Hopital's rule for this. Another thing to point out is that this is a two-sided limit, so I guess we should talk about one-sided and two-sided limits. For a two-sided limit to exist, the left and the right limits must agree, but the function, so for the limit to exist, we're talking about the limit here, for the limit to exist, the function doesn't have to exist at the x value in question. The picture that goes along with this is if I had my coordinate plane and I had some function and then there was a hole and it went on, this is not continuous. However, the limit at x equals a works. I mean, it exists. It's whatever that y value is, like whatever it lines up with. So the y value doesn't have to exist. Or the function doesn't have to exist there for the limit to exist there. So that's something that people always forget. And this is one of the special cases. You might not be given a graph, but I think on the first midterm or the study guide or something, I can't remember what, there was a question that said which ones have to be false or which ones have to be true or something, and then for the limit to exist, for the limit to exist, you need to have the two-sided limit agree, but the function doesn't have to exist. For the function to be continuous, you need the two-sided limit to agree, left and right, and you need the function to be the same number. So that was, I guess we should write down the definition of continuity again. I'll do that because I just said it. For a function to be continuous, the left-sided limit and the right-sided limit and the evaluation of the function as x approaches a or when x equals a, they all have to agree. So there's the difference between continuity and for a limit to exist. The first two conditions are for just for a limit to exist, for a two-sided limit to exist. but if you add in the third condition, then you get continuity. Next are some very, very basic limits that you should know. These are the ones I kept saying over and over at the beginning, like first semester, that you should have these tattooed to your brain. Maybe I said it last year. I don't even remember. It's just the tattoos are there. But for some people, they never. I'm just gonna say them. The first three are when x is approaching 0 for 1 over x. If you think about the graph for this, I remember I had a student, he was just like, I just think about the graph and it's fine. I just think about the graph the whole time. Yeah, okay, so if you think about the graph, then this might be easy, but some people don't. Hopefully you do, whatever. The limit as x approaches 0 from the right side of 1 over x, that's going to be, this gets small, this whole thing blows up, that's going to be negative infinity, because if I'm approaching 0 from the left side, I'm approaching with negative numbers. If I'm approaching with positive numbers, I get positive infinity. Those limits still don't exist, but they tend towards negative infinity or they tend towards positive infinity. These still don't exist, but we can say that we can describe where they go. And then the limit, the two-sided limit, since these do not agree, this does not exist. DNE. So it doesn't equal anything. It strictly does not exist. And then hopefully you should try and think of the other three. If you want to before, I'm going to write them down. Actually, there aren't three more. It's as x approaches infinity, or negative infinity, then what do we get? We get 0. So those ones you should definitely know. Maybe I'll throw in, those are the basic ones. Even if this was just any number, you could always pull the number out in front. Same with all three of these. If these were any number, you could pull it out in front and it would still be the same thing. So make sure you know those ones. I'm going to end this video, maybe make another one. I don't know. I haven't decided. All right, goodbye.